Hi everyone, namaskara. Welcome to Tech Girl Kannada YouTube channel.
Transform and Conquer Approach. Module 3. Work as two-stage procedure. First, in the transformation stage, where the problem's instance is modified to be for one reason or another more amenable to the solution. Second, conquering stage. It is solved. Three variations are there: instance simplification, representation change, and problem reduction. Instance simplification is like transformation to be a simpler or more convenient instance. Then representation change is transformation to a different representation of the same instance. Problem reduction is a transformation to instance of a different problem for which an algorithm is already available. Simple instance or another representation or another problem instance. Problem instance to the solution. Let us go with the heap and heap sort. What is heap? Heap is a partially ordered data structure that is suitable for implementing the priority queue. A heap can be defined as a binary tree with keys assigned to its nodes, one key per node, provided the following two conditions are met. The tree shape requirement. The binary tree is essentially complete. All its levels are full except possibly the last level, where only some rightmost leaves may be missing. Then the parental dominance requirement. The key at each node is greater than or equal to the keys at its children. Heap, which is not a heap because it is the left node is not there. This is also not a heap. Why? In this tree, shape requirement is violated, but in this parental dominance requirement fails for the node with keys. Parental dominance. Here there is parental dominance. Parent should be dominated by the children, but 5 has a children as 6, which is 6 is dominated. Key values in the heap are ordered top down, a sequence of values on any path from the root to the leaf is decreasing. Then the properties of heap set. Here are the properties of heap set. There exists exactly one essentially complete binary tree with n nodes. That is, its height is equal to the floor value of log n to the base 2. The root of the heap always contains the largest element. A node of the heap considered with all its descendants is also a heap. A heap can be implemented as an array by recording its element in the top down, left to right fashion. It is convenient to store the heap's elements in position 1 through n of such an array, leaving h naught either unused or putting there a sentinel whose value is greater than every element in the heap. Heap and its array representation. A heap can be implemented as an array by recording its elements in the top down, left to right fashion. It is convenient to store the heap's element in position 1 through n of such an array, leaving h naught either unused or putting there a sentimental whose value is greater than every element in the heap. That is, which should be stored from 1. H of naught either leaving unused and putting there a sentimental. So if parents are used like this, 10, then 5, 7, 4, 2, 1. A parental node keys will be in the first n by 2 position of the array, while the leaf keys will be occupied in the last n by 2 position. The children of a key in the array parental possession I is like this, and then it will be position 2i and 2i plus 1. The parent of the key in the possession or I by 2. Define a heap as an array in which every element is like this, means h of I is max of h of 2i, comma h of 2i plus 1. Heap bottom up is like this. Bottom up construction of the heap for the list 2, 9, 7, 6, 5, 8. 2, 9, 7, 6, 8, 6, 5, 8. It will be first constructed in this manner. We have found that 7 children of 7th is greater than 7, so we are swapping that first, the last element. Then we have the same manner. Then we have to check this other children. Is 5 less than 9? Yes. 6 less than 9? Yes, true. Is 9 less than 2? No. 8 less than 2? No. Then we are swapping it to the left position. That is 2 should be taken to the left side. Then again considering the left chain, that is 5 less than 2? No. 6 less than 2? No. Then again taking 6 up, we will get this bottom up. With this bottom up algorithm, a heap of size n can be constructed with fewer than 2n comparisons. Max heap is a tree in which value of each node is greater than or equal to the value of its children node. Yes, is a tree in which the value of each node is greater than or equal to their children node. Min heap is a tree in which the value of each node is less than or equal to their children node. So alternate and less efficient algorithm construct to heap by successive insertion. Inserting 10 considering the empty one that is more than that, so we have to swap that element. Again we have to swap another element for that. For delete root key from the heap, we have to delete 9. For that, we are now considering the end value at the top and considering this at the end, other rest all elements in the same positions. Then the 9 is deleted. Then again considering this, we will get as swapping everything. The insertion operation cannot require more key comparisons than the heap's height. Since the height of the heap with n nodes is about log n to the base 2, the time efficiency of insertion is in big O of log n. Heap sort discovered by J.W.J. Williams. This is two-stage algorithm. Heap construction. Construct a heap for the given array. 2 is the maximum deletion. Apply the root deletion operation n-1 timer to the remaining heap. n-2 timer root deletion. First heap construction for the given array. 85 is constructed. 85 for 15, it should be added to the left hand side of the 85, then right hand side of the it will be a 25, then we are having 95. Then we have to compare 95 and 15, which is less, and again that is compared with 85, which is less. So 95 is taken at the top. Then next element is 145. 145 should be added at the right hand side of the 85, but comparing it gives you the less value. Then it is taken over up, and again it is taken up. That is done. Then next number is 55. For 55, it is added till 25. Comparing 25 and 55, it is greater, so swap those things. Then 145, 55, 25. Done. It is correct now. 165. Then 165 and 55 is compared. Comparatively, it is less. So 165 is again taken up and made it as a correct one. Then next is 75. 75 is added at the leftmost corner of the tree, and then it is compared to 15. It is greater than 15, so it is swapped. So this is the tree which we have obtained. Then root deletion, what we do is swapping the leaf node and the root node. Then for this we have to do swappings. First we have to look for the greatest element, that is 145 should come up, so that we will consider to come up first, and then 15, 25 and 55 is considered. 55 is greater, so 55 made up, and then 15 is there. Then again root deletion, 145 should be deleted, so swap 15, that is the last node of the tree, end leaf node. Deletion of the root, end leaf node is like this. 145, then this, swapping both of them. Then we have swapping, it gives you this value, then the root is removed. We have to compare with the larger value, that is 95, 15, that is compared. Then 15 and 70, 15 and larger value is 85, so 15 and 85 is compared, then 85 is kept there. Then again the 95 and the bottommost node, bottom rightmost node is 25, that is swapped with the larger value. Then if we consider that is removed, then 25 is compared with the larger value, that is 85, then that will be swapped. Then 25 and 75 is compared, that will be swapped. Then the last node is 15 and 85 is compared, 85 is swapped. After swapping we have this, and 85 is deleted, and in this 15 and 75 is compared, then it is swapped. Then 15 and 25 is compared, then it is swapped. Then at the next step we have root node as 75 and the bottommost node as 15, that is 75, 15 is swapped and again removed root node. So for 15 we have 55 should come up, and then 55 and 15 is swapped again, then 55 is removed, 15 for 25, then that also 25 and 15. will be swapped. Then comparing this 25 and 15, swapping that because 25 is the root node. Then remove 25, we will get only 15 in that case. Time complexity of the heap sort is theta of n log n. In place sorting happening in this algorithm, it is not a stable sorting method. Heap sort runs more slowly than the quick sort because of the random inputs, but is competitive with merge sort. Maximum key deletion from a heap. One, exchange the roots key with the last key of the heap, decrease the heap size by 1, then heapify the smaller tree by shifting k down the tree exactly the same way as the bottom up heap. The efficiency of deletion is determined by the number of key comparisons needed to heapify the tree, that is, after the swap has been made, and the size of the tree is decreased by 1 since it cannot require more key comparisons that twice the heap's height. The time efficiency of deletion is O of a log n. Deletion is O of log n, but heap sort is theta of n log n.
Thank you for watching. Do like, share, and subscribe to my channel.